really relay the message that shadows are really important for depth perception. But I'll go over it if somebody wants to towards the end. For now, I want to get to the punchline here. And everything I've said so far, aside from the two cues that had to do with eye movement, could be done literally with one eye. You need a single retinal image to be able to extract all I showed you was a single image, right? And all of that information was there. So that means that you don't need two eyes to do all of those things. So the question is, why do we have to if we don't need two eyes?
If one fails, you have another one, a spare one.
Yeah, well, that's from a biological perspective, it's a huge amount of investment for a spare tire. Millions of years of investment to just have a spare tire. We'll see why that is. At least I think, not that I figured it out, but I think I found the answer by just being able to ask some of these pertinent questions. So what you see across the animal kingdom is basically a pair of eyes, like that, or maybe like that on the sides of the head, or a little more colorful from beloved species, mandrill. Or even in the insect world, you have a pair of, in this case, compound eyes, which are made up of individual eyes, kind of rigged together, put together in the form of an array. So each one acts like an independent eye, except that the little brain of that insect takes the information from all of those eyes and uses it to whatever end. The question is, as I said, why two eyes? And if two eyes, where should they be placed? Let's talk about the placement first, and then we'll see why two. The placement is pretty simple. I mean, it boils down to two arrangements. Either the eyes are found in the front of the face with a slight separation along horizontal axis, or they're found on two sides of the face. So you look at some prey animals like rabbits and mice and deer and so on, cows. You look at fish, amphibians, you look at reptiles, they all seem to have that kind of arrangement. Certain kinds of mammals, particularly predatory mammals, the ones that have to eat those guys, end up having frontal eyes, like us. So what is the advantage of having an arrangement like that over that, or vice versa? I mean, each one of them has to have been a successful strategy for it to have lasted this long, 4.5 billion years of supposedly evolution. It all boils down to what you want to achieve. If you want to be more cognizant of what's going on around you, you'd want to put the eyes on the sun. That gives you panoramic vision. You see pretty much from one side to the other side. It's more than 270 degrees of coverage of the visual field, so that these guys don't come and eat you from behind. So you can see where they're coming from at all times. But what happens is, because the eyes are spheres themselves, they only end up having, each one only end up having about 180 degrees of coverage. So what ends up happening is that for eyes like this, you have a little bit of overlap between what's seen by the left eye and what's seen by the right eye. So this is the area that's covered by both eyes. Whereas for an animal, for an arrangement like this, the frontal arrangement, you get a lot more coverage of the two eyes. So what each eye sees is a sliver of the entire field of view, as opposed to what both eyes see in this case. So that seems to basically separate, or be the sort of the deciding force of how you want to arrange. If you want to have that kind of coverage, which is good for depth perception, obviously, otherwise I wouldn't be talking about that right now. Then you would want to put the eyes side by side. If you want to have less depth perception but more coverage of the world, then you want to put the eyes like that. So what is so important about depth perception and its relationship to these two eyes, which has made me leave it from class. It's sort of the punchline of the whole talk. And basically, we're entering this new category of visual cues. In fact, there's just one cue, one signal that is extracted from vision that requires two eyes, vision that's dependent on two eyes. And that's called binocular depth information. It's called stereoscopic depth information. It's called disparity information, or a bunch of other things by different people, different textbooks, different discussions, and so on. And all are referring to the fact that basically something happens to what is seen. Well, something happens to the image as a result of having eyes that are like this. You think that both of your eyes are having an identical view of the world. But that's not true. That's not true. You don't believe me? Hold out your thumb again, if you want. And you look at it with one eye and switch to the other eye and pay attention to what happens to stuff behind it. The whole world shifts left and right, left and right. And as it does, it's basically telling you that each one of your eyes is seeing a slightly different view of the world, that they're not identical views. So that apparently is a rich source of information for animals like us. I don't want to offend anybody. As opposed to animals like these guys. We have this frontal eye arrangement allowing us to do this kind of, allowing us to have this kind of coverage, and as a result of it, we end up having better, what we call binocular disparity. This is the difference in the image between the two eyes, and the way, without getting into too much of the science of this, the way you can measure this is by basically taking, literally measuring tape the size of the eye, and going inside and measuring the distance of corresponding points to let's say, a frame of reference in the eye. Let's define an area or a point, a single point in each eye as a reference point, and then we'll see how far each object's image is to that point by comparing the two eyes. And for most part, these objects end up being on non-corresponding points. They have different distances depending on which eye you look at. I'll give you an example, but just so that you have something to work with, you don't want to use my crude method of testing your binocular vision. This is an example of sort of an everyday scene that is seen by two cameras placed side by side, one next to the other with a slight separation. Now, to most people, these are identical, right?
No.
Except to you guys. So you know what I'm going with, right? Now the object, the content is the same, but the relative position of the items seems to be slightly offset depending on which image you look at. So let's take this big cactus in the front and its relationship to the window. Here, it seems to be covering part of the window ledge or the side of the window, whereas here